Hello everyone. In this lecture we'll discuss a little bit more basic sciences and we'll understand how buffers work. Your body makes quite a bit of acid every day and you also lose bicarb. So to maintain the pH, your body needs a constant supply of buffer. Your body usually makes two types of acid: volatile acid like carbonic acid, which is your CO2 that is formed from your metabolism of glucose, and non-volatile acid such as hydrochloric acid, sulfuric acid, etc. Most of the volatile acid comes from metabolism of fats and carbohydrates. Your body makes around 15 to 20 moles of CO2 every day, and this is cleared by your respiratory system. Metabolism of your amino acid like cysteine and methionine produces sulfuric acid, and amino acids like lysine, arginine, histidine make hydrochloric acid. Aspartate and glutamate makes bicarbonate. You also eat acid in the food in the form of phosphate. So these two are non-volatile acid and these are excreted mainly by kidneys. Meat eaters generate more non-volatile acid than vegetarians. You also lose some bicarb in stool, and there are other forms of acid like in diabetic ketoacidosis, beta-hydroxybutyrate, and lactic acid in hypoxia. Your body handles acid in three ways: buffer system, respiratory system, and renal system. Buffer system is the fastest, taking seconds to a minute to activate to maintain your pH. Respiratory system works in minutes to hours, and renal system in days to months. Bones are also a buffer system for your body, and your hydrogen ion exchanges for calcium, but this is a very slow process. The buffer system is the first line of defense against changes in pH. So for example, if you encounter an acid, first thing you need is a base like sodium bicarb, and this is generated by your kidneys, and the carbon dioxide that is produced by this reaction is excreted through your lungs. So you need both kidneys and lungs for proper functioning of your buffer system. In humans, the buffer is present both extracellular and in intracellular compartments. Extracellular compartment is the bicarb buffer, which everybody knows about. Intracellular buffers constitute of phosphate and proteins rich in histidine can buffer hydrogen ions pretty well, for example, hemoglobin molecule. You also have some degree of bicarb buffer intracellularly as well. Total buffering capacity is divided approximately equally between the two buffer systems. For example, if you give somebody a strong acid, 15 to 20% is buffered by the blood, 30% by interstitium, and 55% by intracellular buffers. Whenever you put acid in an aqueous medium, it is going to equilibrate into its ionic and non-ionic forms, and you get a dissociation constant, which is the concentration of your ionic form divided by non-ionic form. So for example, hydrochloric acid has very high Ka because most of its non-ionic form dissociates into its ionic form, while carbonic acid has low dissociation constant because it does not dissociate completely. So you have quite a bit of non-ionic form left in the solution. So if your alpha is the degree of dissociation and your initial concentration of acid is C, the final concentration will be C multiplied by 1 minus alpha. That gives your dissociation constant equals initial concentration multiplied by degree of dissociation square divided by 1 minus degree of dissociation. Water also dissociates into hydrogen ion and hydroxyl ion. So you have a dissociation constant of water which is equal to H plus multiplied by OH minus divided by non-ionic form of water. Since the concentration of water is nearly constant, Kw is the ionic product of water, which is multiple of hydroxyl ion and hydrogen ion, and that is equal to 1 multiplied by 10 raised to a minus 14. And this gives us our pH scale. pH is defined by negative log of hydrogen ion concentration. So if you have got high level of hydrogen ion concentration, your pH will be low, and if you have got no hydrogen ions, the pH will be pretty high. So if your H plus is less than OH, you have got basic solution, and if you got H plus more than OH, it is an acidic solution. And if both are equal, it's a neutral solution. Kw is 1 into 10 to the power minus 14. The concentration of hydrogen ion in water will be 10 raised to the power minus 7. So the pH, which will be negative of log of 10 raised to the power minus 7, which is equal to 7, and that gives you the pH of water. Let's figure out pH of a 0.01 molar solution of acetic acid with a dissociation constant of 1.8 into 10 raised to the power minus 5. Since H plus ion concentration will be equal to acetate ion, you can write H plus ion as under root of dissociation constant multiplied by concentration of acetic acid, and that gives you pH of 3.37. To figure out pH of 0.01 molar solution of hydrochloric acid, now hydrochloric acid dissociates completely in water, so you will get 0.01 molar concentration of hydrogen ion, and that gives you pH of 2. So what are buffers? Buffers are the solution which resist any change in pH value on dilution or addition of acid or base. And there are two types of buffer solution, acid buffer and basic buffer. Acid buffer is the one which is used by the human system. It is a combination of weak acid plus salt of weak acid and strong base, for example carbonic acid and sodium bicarb. Basic buffer solution are solution of weak base plus salt of weak base and strong acid. So let's see how buffers work. We have solution of carbonic acid and sodium bicarbonate. We know that carbonic acid dissociates weakly into bicarbonate and hydrogen ions, and carbonic acid also equilibrates itself pretty rapidly with CO2 and H2O. Sodium bicarb, on the other hand, is highly ionized, and most of it is in bicarb and sodium ion. Ionization of sodium bicarb will suppress further ionization of carbonic acid through common ion effect, because as your bicarb ion concentration is higher, the reaction would be shifted towards the left, towards the formation of carbonic acid. So we'll have small level of hydrogen ions and large concentration of bicarb ions. So let's see how this solution fares in acidic and basic media. If you add a lot of H plus ions, that is acid, this will combine with the bicarb ion and will form carbonic acid, which will be equilibrated by your respiratory system. So your H plus ion will remain constant. If you add hydroxyl ion, this will combine with your carbonic acid to form bicarbonate ion and water, and therefore your hydrogen ion concentration will remain the same. I would like you to remember this concept very well, because you will need it in understanding why giving bicarb pushes do not work all the time, and why you need a good respiratory system function to maintain your pH. The pH of acid buffer is given by pK plus log of salt by acid. And pK is the dissociation constant of your weak acid. Buffers work best when the solution are present in equivalent amount. That means molar ratio of salt to acid is equal to 1. And the best buffering occurs when pH equals pKa. Let's do some example to understand how effective is this buffer system. Let's take carbonic acid and sodium bicarbonate of 1 molar concentration. That gives your pH equals 6.1, since your carbonic acid and bicarb are in ratio 1:1. And at this pH, the bicarb buffer works the best. If you add 0.1 mole of hydrochloric acid into this buffer, you will use the bicarbonate and convert it into carbonic acid. So your bicarb concentration will fall from 1 to 0.99, and your carbonic acid will subsequently increase to 1.01. And when you plug this into your pH equation, your new pH is 6.09. We worked this up earlier that if you add 0.01 mole of hydrochloric acid in water, the pH will be 2. So you can already see that the change in pH was only from 6.1 to 6.09 and did not drop down to 2. Similarly, if you add 0.01 mole of sodium hydroxide, your final concentration of carbonic acid will be 0.99 and bicarb would be 1.01, and your pH will be 6.11. Otherwise, your pH would have increased to 12. So you can see that buffer solutions are really good at preventing massive changes in pH. The buffer system used by humans is your carbonic acid and bicarb buffer, and we use Henderson Hasselback equation. In this case, your pKa is the dissociation constant of carbonic acid, log of which equals 6.1. Since your carbonic acid equilibrates pretty quickly with the level of CO2 through the carbonic anhydrase, you can change the denominator of acid into solubility constant multiplied by the partial pressure of carbon dioxide. Since solubility constant of CO2 is 0.03, you get your favorite Henderson-Hasselback equation. pH equals 6.1 plus log of bicarb divided by 0.03 into pCO2. In humans, since the ratio of bicarb to pCO2 is close to 20:1, therefore log 20 equals 1.3. That gives your pH of the blood to be 7.40. Since Henderson-Hasselback equation is a little difficult to work with, we'll try to take the log out, and if you take anti-log of this equation, you get this equation. And since your Ka equals 800, you get a very simple equation, that is your hydrogen ion concentration equals 24 times PCO2 divided by bicarb. And this is very simple equation to remember because you know that your bicarb levels are around 24 and that gives your PCO2 to be 40. Since pH of 7.4, you have 40 nanomole per liters of hydrogen ions. Take a moment to understand this equation and you will realize that this equation is very simple to understand and will help you further when you interpret your ABG. For practical utility of this equation, please watch my video on ABG interpretation. So in summary, buffer is a solution which resists any change in pH value on dilution or on addition of acid or base. Buffer system is the first line of defense against changes in pH, and you have both extracellular and intracellular buffers. Extracellular buffer is your bicarb, and your intracellular buffers are phosphate and proteins like hemoglobin, etc., though some form of bicarb buffer also exists intracellularly. In humans, the commonest extracellular buffer is your weak acid plus salt of weak acid and strong base, that is your carbonic acid and sodium bicarb. And using Henderson Hasselback equation, you can figure out your pH equals 6.1 plus log of bicarb divided by 0.03 multiplied by PCO2. However, you can simplify that into this equation where your hydrogen ion concentration equals 24 times PCO2 divided by bicarb. We'll use this equation in our interpretation of our ABG lecture series, so make yourself familiar with this equation. Thank you.